So yet another vacuum tube oscillator, this time with a fancy tube. This tube is a FU811J, maybe J, I'm not sure. It's Chinese and brand new, but I'm not sure if it's NOS or made nowadays. Anyways, this oscillator is a single-ended. It doesn't use a tank capacitor for being cheap. Apart the tube, anything is quite cheap here. The capacitors I'm using are absolutely not relevant in value and quality. And I'm using a coil with a high number of turns to have a low frequency. I calculated the frequency very badly to be 20 MHz, but it came up to be like 11 or slightly more. And why? Because apparently, being a triode, not a pentode, the interaction between the grid and the anode makes the frequency lower if you base yourself on the stray capacitances of the tube. Anyways, as grid leak network, here I'm using as resistor a 25 watts light bulb halogen, and this lights up also because the power for the grid is a bit high, because this triode needs a bit of biasing, positive biasing on the grid. Okay, let's try this thing. This thing is fairly powerful. This oscillator is fairly powerful, and you'll see. Let's turn on here the filament. Nice. Cool, huh? I love it. Anyways, and variac. I'm powering this thing with a maximum. Let's turn on the multimeter. God damn you. I'm powering this thing at 600 volts. That is the maximum that this power supply is capable of. Anyways, let's crank the power. Okay, 100 volts, 200, 300, 400, and the light bulb turned on. 100 milliamperes of consumption, more than 600 volts. Fluorescent tube near the anode. And it lights up. And it stays on a distance at a pretty far distance. And it's off. No red plating, luckily. Okay. MTX90. Ooh. I feel heat. This is the anode connection. The anode is just connected to the coil, no other things on the anode. And inductive coupling. You have this light bulb here, 3 volts with a single turn. And it lights up. Okay, let's bring it down. And okay. So I forgot to show you some arcs, small arcs with an insulated tool, metal tool, but insulated. Let's bring it again to 600 volts. And 100 milliamperes of consumption. Let's pick the tool. Let's see. Okay, the arcs are very small, but these are high frequency arcs. And the light bulb flickers. Okay. So what I'm doing here, I'm driving this fluorescent light with a system similar to a fluorescent electronic ballast, but with an adjustable frequency, fixed frequency, and maybe also an adjustable voltage. So what we have here as a setup. First of all, we have a power supply with a transformer. This transformer puts out 60 volts SC. and go on this bridge and capacitor here to make kind 85 volts DC that go on this half bridge driver here. This driver is an old friend, it's wimpy, it has small components, it's a bootstrap mode driver, so it doesn't have a gate driving transformer, and it has adjustable frequency on these two potentiometers here, fine and coarse, but not by much, and the frequency is adjustable from like 3 kHz to a maximum of like 78 kHz. The other side of the driver here is made with these two electrolytic capacitors to make a middle voltage. And we have also frequency reading here on this digital multimeter and current reading on the supply of the circuit with this analog multimeter that is 250 milliamperes full scale, but it will not rise much. The output of the driver are these two wires here. The white one comes from the middle of the two electrolytic capacitors and it's a fixed voltage. The other wire instead is the switching connection and it will swing from a maximum of like 42 volts to a minimum of like minus 42 volts. This drives this system here. Sorry for this assembly, but it's quite temporary. Anyways, and it's basically the output of an electronic fluorescent ballast with tube or a CFL bulb, the output, and it's this inductor here in series of the circuit, and this comes from a CFL bulb. It's 3.2 millihenries and it's gapped. The other side of the tube has this capacitor here. This capacitor is 5 nano6 in value, high voltage, and it's bigger than the capacitor you find in a CFL bulb. Why? Because I wanted a lower frequency, lower resonant frequency, because otherwise the driver can't cope with the frequency. And that's basically it. Okay, let's try this thing. Little note, this network with the tube here has kind of three states. There is the state that it's off, the state that the tube is conducting with the gas, and the state that the cathodes are hot. Okay, logic supply on. We have 3 kHz and power on. We don't have a current consumption on the multimeter. Let's raise this potentiometer here and we have kind of 11 kHz. Again, not enough for the resonance. Let's crank the frequency more. 15 kHz. 18. 20 kHz. 30 kHz. Okay, now we have the glowing of the cathodes and it's struck. It was too fast. And at 3 kHz, the current consumption is maximum and the tube is quite bright. Okay, instead we go past the frequency, we reach kind of 78 kHz and go down instead. 40 kHz. Okay, now it does this odd thing, not always. Apparently the high frequency at 40 kHz ionizes the gas on one side of the tube, just one side, and the other side instead the filament is glowing. Let's go down a bit more. More glowing, and it's struck. 39 kHz. Let's go down. The current goes also down, but there is a bit of roller coaster because of a lot of states of the system. And now instead going down in frequency. It's something odd. Now at 3 kHz it doesn't draw anything. Again 11 kHz, no conduction because the tube is not struck. Let's raise again the frequency. Let's reach kind of 34 kHz. These potentiometers are touchy. It's not computerized, obviously. Okay. Let's see. Oh, it was too much. Okay. Can you see the cathodes glowing now? Apparently in the video. A bit more. Total resonance at like 37 kilohertz. And it's struck. More frequency and it's off. And at a higher frequency, there's a bit of current conduction because the capacitor conducts at a high frequency. And we are again at conduction. And I can go down in frequency. And sometimes the cathodes are hot and the current increases and the brightness increases, sometimes not. Okay, now 11 kilohertz, and now it's off. So I made another VTTC, this time smaller, as you can see, and with a really small vacuum tube. This is a PCL86, it's a triode pentode, I'm using just a pentode. It's an audio tube, low power, and obviously you can't make a VTTC with a tube like this, but I wanted to try what was possible with a tube of this size and power. And there's a trick for letting a tube like this work. The circuit is a classic VTTC schematic. I'm using here a primary with 41 turns of aluminum wire with just a final turn of thicker copper wire. This thicker wire is used to avoid flashover from the secondary to the primary. The secondary is an old friend. This is like 900 turns of really fine wire wound on a 5 cm pipe. A small top rod and needle. The feedback coil is here inside the coil, and it's on the bottom, and it's like 15 turns of fine wire, copper wire. As a tank capacitor, I'm using here this array of polypropylene capacitors, low value. These are rated for 2 kilovolts each. They are in series of 2, so theoretical 4 kilovolts, but more. And they sum up to be like 800 picofarads in total. As bypass capacitor, I'm using this array of ceramic capacitors here. These are Y1, stupid stuff, and these sum up to be 4 nanofarads, and they are in series of 2 to withstand a higher voltage. Regular micro oven diode, nothing fancy. For the grid 2 of the tube, I'm using just a resistor from the B+ anode supply of the circuit directly this way, and this system seems to be the best for this solution, for this setup. I'm using an high frequency trap that is mandatory in this case. I'll explain you why later. As grid link network, I'm using these resistors and capacitor. The resistors sum up to be 4K in value. The capacitor is 2 nano 2. And other things, this is the MOT that I'm using. It's the smallest that I have. This is the filament transformer, overkill transformer for the filament. And 1 Hz staccato with a relay on the primary of the MOT, and variac. And that's basically it. Okay, let's try this thing. The cathodes are hot of the tube, so the filament is already on. Staccato controller, variac, and let's see. Okay, this is 30% variac, kinda 40, kinda 50, kinda 60, kinda 70% variac, kinda 80% or 90, more, and we are at maximum. Ooh. Okay, let's crank it down a bit. Let's wait. And let's crank it up again. A bit of popping. But why? Cranking. Maximum. And it's almost 20 centimeters. Kinda 18 centimeters. Okay. And off. So how is it possible to make a coil like this with a vacuum tube so ridiculous? Well, first of all, vacuum tubes are like theoretical components, like in a simulation, like a computer simulation of a circuit, because the datasheet says a bunch of things like maximum current, etc. But at pulses, a vacuum tube can withstand like tens or hundreds of times its rated current, power and voltage maybe. Yeah, this tube doesn't have an anode connection on top far away from the other pins. Anyways, but the trick is also that when you assemble a coil like this and you raise the power, the tube will obviously make popping sounds and flashes inside. And when the flash happens, the arc strikes inside the tube. This is because there are sharp spots in the metal, and the arc inside the tube rounds these sharp spots. So you crank down immediately the variac to avoid that the hot spot makes again an arc and ruins the tube. But when it cools down, you can crank again up the variac and pass that point, because now the sharp spots are rounded and the tube withstands a higher voltage. And this tube popped like 20 times, I don't remember, and now it's, let's say, ready for a high voltage, but it still pops sometimes, because you know, well, I mean... So, yet another vacuum tube oscillator. I'm trying to make these things as cheap as possible. In this case, I have just trashy capacitors, trashy resistors, and a trashy tube. Maybe because I want to make this project as something that can be proposed elsewhere, I don't know. Anyways, in this case, I'm using a PCL86 as tube. This tube is damaged and old and very used, and you can use a PCL82, PCL85 as well, or a PL84, like I'm using here, the tube, and you can see those blue spots that are nice. The circuit in this case, compared to other oscillators that I made in the past single-ended, is kinda simplified. In fact, I'm using as a tank capacitor the stray capacitances of the tube. It's just the pentode, the power pentode. The triode instead is disabled, it's all grounded, all the electrodes are grounded, and it's an audio tube. And this thing runs at 74 MHz with an audio tube that is also damaged, probably the filament on the cathode discharges or something. Anyways, because it makes popping sounds on the speaker. Anyways, to use just the capacitances of the pentode of the tube, the tank coil here is connected simply on the anode here, and there is nothing else connected on the anode of the tube, just the coil. And also the feedback coil here is smaller. This because I wanted to match the resonant frequency of the output section and the input section, because the input section on the grid has a higher capacity and I'm using a smaller coil to match kind of the frequency of both the input and the output. Anyways, you have to excuse the mounting base here because I didn't have a second wood slab at end when I made this thing. Okay, let's try this thing. Let's read the frequency. The cathodes are both hot, but we need just a pentode. Okay, let's turn on the variac and let's give, let's say 150 volts. Okay, that's enough. And we have the probe here, magnetically coupled. And let's see. It says 74.5 megahertz. Okay, now let's crank a bit more the power. Let's bring it to 250 volts. I have here this shorted light bulb, 3 volts. Let's see. And it's magnetically coupled to the oscillator. Just one turn, one poor turn. Okay, and it's not even at the maximum power. Now let's bring it to 400 volts. Okay, now up power run. Again, the cathodes are hot. Let's turn on the variac and let's bring it briefly to 400 volts. Okay, we have this fluorescent tube. It stays on also at distance. Okay, and this MTX90 on the anode of the tube. Okay, let's crank it down because the tube is quite stressed. Sorry I didn't show you the current consumption, but it was 50 milliamperes here. So thanks for having watched my video and bye!